Hello, everyone. So tonight I'm just going to do a couple of problems in static equilibrium, and you'll see them there. And I'll look over every once in a while into the chat to see if there's anyone asking questions. Otherwise, I'll just proceed to do the problems. Let me take a quick look to see what's happening in the chat. Oh, a couple of people. Okay, well, let's begin. The two questions, one of them is easy and then the other one's a little bit more demanding. The first one is a lever problem, and levers are about the easiest problems that you can have in static equilibrium. And so let me read the problem and then we can do it. A lever is made as shown. I'll show you that in a second. I got to switch to the other screen. Its mass is 15 kilograms. If the mass is 15 kilograms. Well, you don't see the mass yet. You will in a second. Find the applied force and the force applied by the fulcrum. Okay, so let's switch over to this whiteboard right here. So what you're seeing here is a lever, and this triangle over here is a fulcrum. And basically, the lever can pivot about this point here like that, and here's that mass, which is 15 kilograms, and this arrow here is indicating a force. Okay, so we want to find what force we have to apply here to keep this stable, and the other thing we want to know is how much force is applied by the fulcrum on the lever as well. Okay, obviously if this fulcrum weren't here, this side of the lever, you can imagine it's like a board or something, would just fall. Okay, so in static equilibrium, there's a few criteria that have to be satisfied. First is the sum of the forces have to equal 0. And the reason for that is if the total force isn't equal to 0, then what will happen is the object will start to accelerate because of Newton's second law. But that's not enough because these are extended objects, rigid extended objects. If the torque is not 0, then what will happen is the object will start to rotate. It'll start to angularly accelerate. Okay, so both of those have to be true. Both the sum of the forces has to equal 0, and the sum of the torques have to equal 0. Okay, so the first step is to draw a free body diagram. Now, what I have here is not a free. It's a diagram. It's not a free body diagram, but I can draw the free body diagram on top of this because all you need in the free body diagram is just the forces, okay, and where they're acting on the object. All right. Let me do the forces in red. You can take a look here and you can say, well, what forces are acting? Well, one force, the force you should probably just start with, is the force that's acting on the this mass right here, and that's gravity straight down like that. Okay, and that's going to equal mg. All right, and m we said was 15 kilograms. All right, and g we're going to round off to 10 like we did last semester. All right, and so this is going to equal 150 newtons. All right. The next force that we can look at, I guess I've already got it drawn in here, but I could just highlight it in red, is that force right there. This is the applied force. I could be trying to lift this with like my hand or something like that, and we'll just call that FA for applied. And we don't know how big that is. In fact, that's one of the questions that I've asked. Okay, and then the other force is going to be here at the fulcrum, and it's got to be upwards like this. Okay, and we can call that F subscript F. Okay, that little F there for fulcrum, which is this red triangle down here. Okay, so there are all the forces, and the next thing is to make sure that they all add up to 0 and the torques all add up to 0. The first thing you'll notice is that we really only have the value for one of them. Okay, so we don't know that value and we don't know that value. All right, and what that means is that the sum of the forces is not going to be sufficient. All right, so let me switch back to my other screen here. Let's start right here. Let me see if you can see that. Yep. Okay, so sum of the forces must equal 0. All right. Now, because this is because forces are a vector, it's both the sum of the forces in the x direction and the sum of the forces in the y direction. So if I switch back just very quickly here to the white screen, I could set up a coordinate system. Let me draw it over. Let me draw it over here. Where I have this is like the x direction, and up is the y direction, like that. Okay, but you'll notice that all the forces are either up or down. Okay, and so in this case, all of the forces are in the y direction. Okay, either parallel or anti-parallel to the y-axis. There are no forces in the x direction. Okay, and so when we go ahead and make use of this, some of the forces, you'd have to do actually some of the x components, and of the forces is equal to 0, and the sum of the y component, component of the forces is equal to 0. I can't type. Okay, there we go. But as I said a minute ago, there are no x components. Okay, so we don't have to make use of that at all. All we really need to make use of is this one right here. Okay, so sum of the y components. Now let's switch back very quickly to that diagram and take a look at what we have. We have downwards, we have 150 newtons. Okay, so that means that the total force upwards has to also equal 150 newtons. Otherwise, the object would either start to accelerate up or down. Okay, and there are two forces up. There's the fulcrum force up, and then there's the applied force up. So both of these forces together must balance that 150 newtons down. Okay, so over here, what we'll do is we'll just say, all right, there's the force of the fulcrum that was up. Actually, we could even write it this way: sum of components up must equal sum of components down. Okay, so the force is up, sum of, I guess we should say force components here, because there's also going to be the torque in a minute, but sum of the force components up must equal the sum of the force components down. And there was the fulcrum force up, and there was also the applied force that was up, and that has to equal the 150 newtons down. Okay, and there's our first equation. Okay, and as I said a minute ago, there are two unknowns there, and so you can't solve it by just balancing the forces. Okay, that's not going to work. All right, so you need the torques. Okay, so back to the diagram. How do you determine the torques? Well, the formula for the torque, maybe I should just write that down. Let me write it over here. Tau is equal to RF sine theta. Okay, that's the formula for torques, to calculate a torque. Now, each one of these forces, so that force, this force, and that force, all three of those forces, each one of them can have a torque associated with it. Okay, and you have to just calculate RF sine theta for each one of them, and worry about whether they're clockwise or counterclockwise. We'll get to that in a second. But then when you add them all up, the clockwise torques have to balance against the counterclockwise torques. Okay, so let's go ahead and do that. But the first thing you'll notice is this R. Okay, so let's say we're going to calculate the torque due to the fulcrum force. Okay, so you'll see here there's this R, and you go, well, how do you calculate the R? Well, the R is the distance from where the force acts on the object, and the force is acting on the object right there where I'm making that big red dot. Okay, from there to the axis of rotation. And the thing is that there is no axis of rotation, because if you're in a static equilibrium case, there is no rotation. So if there's no rotation, there's no axis around which that rotation can occur. And so this leads to this idea that you have a freedom where you could choose the axis of rotation wherever you like. Okay, and you want to choose that axis. Like you could choose it anywhere. Like literally, you could even choose it right there outside of the, not even on the in the line of the board or anything like that. You could choose it over here. Okay, I mean like literally anywhere. Let me actually use purple, a different color. Okay, you could choose like the axis of rotation right there. But those are silly choices. What you want to do is you want to pick one of the unknown forces. Okay, so that's an unknown force there, and that's an unknown force there. You want to pick one of the two and say wherever that force is acting, let me put the axis of rotation there. Okay, so I'm going to put the axis of rotation at the fulcrum. It kind of makes sense because if you were to allow this to move, the axis of rotation is kind of like where the hinge is, but you don't have to choose it there. Okay, but if you do, what that means is that when you go to put your value for R here for FF, that's going to be 0. And so then the torque due to FF, let's call it the torque due to the fulcrum, with this choice right there, okay, with that choice of the axis, it's going to be 0. Okay, and so that R is, because that R is 0, because the force is acting right where the axis is. So you're asking the question, how far is the force acting from the axis? 0. Okay, well, if the force is acting at distance 0 from the axis, then R is 0, and so then that torque is 0. Okay, and that makes one of the unknowns go away. Okay, you'll see that in a second. All right, there's this one here, the force due to the weight, that one there, and it's acting at a distance of 2 meters from the axis of rotation. Okay, it's 150 newtons, but acting at a distance of 2 meters. And there's also this force, okay, and it's acting at a distance of 2 plus 3 meters, or a distance of 5 meters, all right? And so these two forces, this one and that one, those are the two forces that will give you a torque. This one, the fulcrum force, doesn't. And the other thing you'll notice is that these two forces, so imagine that you allow the object to rotate around that axis of rotation. The fulcrum force wants to make the lever turn this way. Okay, so what direction is that? That's counterclockwise. Whereas the weight force, this one here, wants to make this turn that way around the fulcrum. So imagine that, this is fixed at the fulcrum here, and you're pushing down, or gravity's pushing down. That would make this want to turn clockwise. So one force wants to turn the object clockwise, the other one wants to turn it counterclockwise, and you can see that the two torques will cancel against one another. Okay, so that has to be the case, because, and let me get rid of those two. If this torque were big and that torque were small, like that, well then this torque right here would win, okay, and the thing would turn counterclockwise. And the other possibility is if this torque is small, whoops, wrong way. This torque is small, and this torque is big. Well, then it would want to turn clockwise. The only way that this is not going to turn either clockwise or counterclockwise around the axis of rotation, whoops, around the axis of rotation, which is right there, the big purple dot, is if that torque due to FA and this torque due to mg exactly cancel one another. Okay, and so there's the the criterion that the torques have to add up to 0. All right, let me switch back to this and let me do that one. So now we have sum of torques clockwise must equal sum of torques counterclockwise, like that. Okay, and the clockwise torque, that was, well, let's switch back just very quickly. Whoops, wrong screen. The clockwise torque, that was mg, right? Because here, let me draw it in there. That wants to turn it this way. Okay, so again, what you're doing is you're picturing that it rotates around that axis right there, and if you're pushing down, this thing will want to rotate that way. Okay, so the clockwise torque is due to the 150 newton. All right, gravity. All right. So over here, the clockwise torque, what's the formula? R F sine theta, like that. Okay. And of course, that's got to equal on the other side also R F sine theta. But this one is due to the fulcrum. Okay. And this one is going to be the applied. Okay. Because it was the fulcrum. Oh, sorry, not the fulcrum. The force due to mg there, like that. I guess we could just write. What shall we write? Let's just write mg, fmg, like that. So the weight of the mass that wanted to turn it clockwise, and the applied force that wanted to turn it counterclockwise. Okay. So let's go ahead and plug in the values here. So for the weight mg, that was at a distance of 2 meters. Let me show you that again. So starting at the fulcrum here to where the weight is, that's a distance of 2 meters. Okay, so this number right here is 2 meters. Okay, the weight mg was 150 newtons, like that. Sine, and the angle, that's 90 degrees in this case. But why? So how do you determine the angle? Well, let's see, what color can I use? Let me use red, I guess. No, we used red. Let me use blue. Okay, so how do you determine that angle theta? Right here. So that angle right in there. How do you determine that? So start at the axis of rotation that you chose, and pretend that you're walking from that axis to where the force acts. Okay, so that looks a little bit messy. Let me just draw it down here. Okay, so you're walking from the axis to where the force acts on the object. And then what do? Then you turn and you follow. Let me get rid of that arrowhead. Let me do that again. Okay, you get to here, to where the force acts, and then you turn and you follow the force like that. And you say to yourself, well, what angle did I turn there? And you turn 90 degrees. Okay, so that angle is 90 degrees. This other angle over here, let me do that one too. Get rid of this. So the angle for FA, because we're going to need that one in a minute, start at the axis of rotation, walk to where FA is X, and then turn and follow FA. Okay, and you say, well, what's that angle in there? It's again 90 degrees. Okay, it's basically the angle between the R vector. Okay, so the R vector starts at the axis here and goes to where the force acts. It's the angle between the R vector and the F vector, and that's 90 degrees. Okay, and clean up a bit. And so go back over here. So this one is 90 degrees. Okay, and that's got to equal on the other side. The distance from the axis to where FA acts, that was 5 meters. Okay, maybe I'll just very quickly show you that again. It was 2 meters from the fulcrum to the mass, plus another 3 meters from that mass to where FA acts, for a total of 5 meters. Okay, so that's where I got that 5 meters. And FA we don't know. Okay, we don't know. It's one of the unknowns. And the angle was again 90 degrees. Now, sine of 90 degrees, you should know that one is 1. All right, and that means that what you're going to get here, so I don't know, let me put this up here, maybe get it out of the way. Okay, so what you're going to get here is 2 times 150, which is going to be 300 Newton meters. Okay, and that's got to equal, on the other side, 5 times sine of 90 degrees, which is 1. It's going to be 5 meters times FA. Okay, so notice that the meters cancel out, and you'll just get an answer which is in newtons. So it's going to be 60 newtons. Okay, because 300 divided by 5 is 60. Okay, so there you go. We've answered one of the questions. We now know that what was the question? So the applied force. Okay, all right. So that's 60 newtons. And now sub into equation number 1 here. Let me just rewrite equation number 1. Okay, and we have FF, which is still unknown. FA we now know is 60, and that's got to equal 150 newtons. And so that FF is going to equal 150 minus 60, which is 90 newtons. Okay, And so that answers the problem, right? Let me go back to the diagram here and write in those numbers. So now we know. I guess I can write this in purple here. We now know that the fulcrum is, actually I forgot already, is 90. Okay, so this one is 90 newtons, and this one was 60 newtons. All right. And of course, the other one was 150, but we knew that to start with. All right. So there you go. There are the three forces: that one, and that one. Now, I'm not going to do this, but if you want later for practice, instead of putting the axis of rotation right here, okay, you could put the axis of rotation here at the mass, or you could put the axis of rotation there at the applied, and you'll still get the same answers. Okay, now the formulas will look different when you do them. The torque formula will look different, I should say, but it'll still work out. Okay, I don't want to do it right now because it's kind of trivial, but try that on your own for exercise. All right, so there we go. There's our first problem. That was a bit straightforward. Let me take a look here. Okay, nice. We have 4 people watching. So I don't see any questions, so I'm just going to go on to the next one. Okay. All right. So this is our second problem for the evening, and it's a ladder problem. Okay. Now I did another one which was a sign being held up, and I don't think it's important to do another one of those, but you could expect on a test or an assignment to see one like that. But I think the ladder problems are a little bit more difficult, and so let's do that one. Okay, so what do I have here? I have a 20 kilogram ladder. Okay, and it's going to lean up against the wall, and the base of the ladder is going to be 4 meters from the wall, and the top of the ladder is going to be 5 meters above the ground. Okay, I've got a diagram in a second, but so we got this ladder. It's 20 kilograms. The bottom is out 4 meters from the wall, and the top of it is 5 meters from the ground. Now, this part is a little bit different than what I did in the lecture. Okay, I'm going to assume that the ground is very smooth. Usually that's not the case, okay? Usually the ground has a lot of friction. But let's assume that the ground is very smooth, like maybe it's ice or something like that, okay? Now, as you can imagine, if the ground were smooth and the wall smooth, there's no way this ladder is going to stay up, okay? So there's no friction between the ladder and the ground, but there is going to be friction between the wall and the ladder. Okay, now this is not usually the way ladders work, but let's do it. During the pre-recorded lecture, I had the friction between the ground and the ladder. Okay, but we're going to do it this way. Okay, and what do I want? Well, I want all the forces. Okay, so what forces? The force between the wall pushing back on the ladder, and that's going to be straight up because there's no frictional forces either way. All right, either to the left or to the right. Okay, and sorry, I said the wall. The wall. There's going to be 2 forces. I apologize. The wall is going to be pushing out, and there's also going to be a frictional force up. Now I'll draw that in a minute. The ground is going to be pushing just up because there's no left or right force because there's no friction on the ground. Okay, so those are the forces that I want. Let's take a look at the diagram here, and let me switch to. There we go. There's our ladder. Let me see. Okay, good. You can see that. All right. So you can see the ladder there, and the ladder is leaning up against the wall, and of course it's being held up on the ground. And the top of the ladder here is 5 meters from the ground, and the bottom of the ladder is 4 meters from the wall, like that. Okay. And the ground is slippery. It's the wall that has friction. All right. So first thing is what forces are acting. Okay. So the ground is going to push up on this, okay? So I guess we could start there. Well, usually I start with gravity. Let's start with gravity. So the ladder has a certain length, and we're going to need that in a minute, okay? But in the middle here, that's where we're going to put the force of gravity. And the force of gravity is going to be straight down like that, okay? mg. There we go. Okay, so the force of gravity acts in the middle. Now, that's the way it works with uniform objects, okay? So I didn't really prove this in the lectures, and I'm not going to prove it now. Technically speaking, gravity acts all the way along the ladder. Like there's a little bit of gravity all the way along the ladder here, because there's mass. Wherever there's mass, there's a force of gravity. But for these kinds of problems, you can pretend that all of the gravity is acting as if it were acting at the center of mass, and of course straight down because gravity pulls down. Okay, so there's our first force that we've identified. Okay, the second force is the ground on the ladder, and it's going to push straight up like this. Okay, and we can call that F, and I'll call it capital G for ground. Whoops, capital G for ground, because little g usually means gravity. Okay, now because there's no friction with the ground, okay? See, the ladder would like to slip out. It'd like to slip to the left. If there were friction with the ground, then there'd have to be a frictional force that way, okay? So you can see that horizontal force that I just drew, okay? And that's what I did during the lecture. But right now, I'm saying that in this problem, I'm saying there's no force of friction with the ground, and so that's not there. Okay, and so you're saying, well, why doesn't this thing slip? And the reason is because there's going to be friction up here. Okay, so the wall, what's it going to do? It's going to push out on the ladder. Okay, you could call this like a normal force. Maybe we will. We'll just call it a normal force like that. It's technically the normal force due to the wall, like FWN or something like that, but this is good enough. But the other thing is because there's no friction here, and because the ladder would like to slip out that way, right? Okay, then there'd better be some friction here up like this. Okay, we can call that FF. And again, that's friction, but friction due to the wall. Okay, so there you go. That's what's going to keep the ladder from slipping down. Okay, that's what's going to keep the ladder from slipping down. That FF. If it weren't for that, then the ground here wouldn't be able to hold it in place. And let me draw this in blue. This thing would slip out that way, and of course this part would want to slip down like that. Okay, so because it isn't slipping, then there must be a force counteracting, the direction. The blue arrow there, I guess, is my acceleration. It'd want to, drop down here, so there'd have to be a frictional force up. Okay? So, there you go. Now, I agree this is a little bit hard to get all the forces, but what you do is, you just have to think through them. You say, well, just like we did last semester, is there gravity? Well, yes, because, the thing has a weight. Okay, what is it touching? Okay, well, it's touching a wall, and it's touching the ground. Okay, wherever it's touching, there's a normal force. Okay, and a normal force means, like let me draw it here in blue. See, if there's a wall here like that, there's the wall. Okay, the normal force is always perpendicular. That's what normal means. It means like perpendicular to a surface. Okay, so you could see here that there's a normal force with the ground and a normal force with the ground. And then the other thing is there any friction? And I told you there's no friction down here, but there is friction up here. Okay. Now the only thing you might have gotten confused with is like, what direction do you draw the frictional force in? And I'll tell you that if you get it wrong, you'll get a negative answer, and you'll know that you chose the wrong direction. But just ask yourself, well, what does that frictional force have to do? It's got to keep the ladder from falling down. Okay, so if the ladder wants to fall down like this, well, then that frictional force had better be up. Okay, so there you go. There's that step. So at this point, we've identified all the forces that are acting on the object. Okay, not only have we identified all the forces, but we've also identified where on the object they act. Okay, and that's a little bit different than when we just did Newton's laws acting on a mass, or like on an inclined plane or something like that. Here, because we got to determine, the torque, and the torque is RF sine theta, right? And so to get RF sine theta, you have to find R. And R, well, you're going to have to measure with respect to some axis of rotation. And so you have to know where the forces are acting so that you can measure R. You're going to be measuring R from the axis to where the force acts. Okay, and so you have to identify where on the object the forces are acting. All right. So there you go. Let's do the sum of the forces first, and make sure that they all balance. Okay. And I just realized that this problem isn't going to work. Ah, geez, sorry guys, I should have probably solved it first. Do you know why it's not going to work? It's not going to work because there is no normal force. See, if this normal force were the only force, then well, let me show you why I just realized that normal force is actually zero. I mean, I shouldn't say it wouldn't work. It's actually not going to work out the way I wanted it to work out. Okay, here's why. Because this normal force there, see, it's the only force in the x direction. If that's the only force in the x direction, then we know immediately that Fn has to equal 0. Okay, well, I mean, I could still solve it this way. Yeah, let's do that. I guess we got one of them already. Okay, so it's just I didn't expect it to be quite that simple, but that's all right. Let's continue. Okay, so let's balance all the forces first. All right, over here. The dangers of not actually solving a problem before you tackle it. Okay, all right. So remember what we said here? We said that the sum of the forces in the x direction has to equal 0, and the sum of the forces in the y direction has to equal 0. Okay, so let's go back to the diagram and take a look. All right, so let's take a look at the sum of the forces in the x direction. Let me put that coordinate system back in there. Whoops. So x will be like this way, and y will be that way. Okay, so we're going to do the sum of the forces in the x direction. Well, what forces are there in the x direction? Okay, there's only one. There it is. All right. And what's that force got to balance? Well, there is no other force to balance. So you know what? The normal force there has to be 0. Okay. So that was a little bit too easy. All right. What about these forces right there? Okay, the sum of the forces in the y direction, they have to add up to 0. Okay. So how do we work out that one? Well, let's, oops, I forgot to show you what I wrote down. Okay, so over here, sum of the forces in the x direction, that's equal to 0. Okay, so sum of the forces in the y direction. Now let's go back to the diagram. So we have two forces up, FF and FG up, and we have MG down. Okay, and they have to balance. Let me actually circle them. Let me get rid of that. So this one has to balance against that one, and has to balance against that one. Okay. So what do we have? Let me switch back here. We have, well, actually, let me go back again. FF up and FG up and MG down. Okay, so remember that FF and FG are up and MG is down. All right, so we have that the frictional force is up plus the force due to gravity. The ground is up. Okay, and that has to balance MG, which is the weight of the ladder. All right. Now what? Well, we actually know what mg is because I told you that the ladder weighs 20 kilograms and g, of course, is 10. So this is going to give me ff plus fg. Whoops, fg. That's got to equal 20 times 10, or that's got to equal 200 newtons. Okay, so there we go. There is the equation number 1. All right, and as you could see, we're in the same sort of a situation as we were up here with the lever. We don't have two of the forces, okay, and so you can't solve it because you don't know the two forces that are acting. Okay, if you knew one, you could get the other. So at this point, you have to make use of the torques. Okay, so the sum of the torques have to be balanced. All right, and so let's go back here to the whiteboard and let's take a look. What what where are we going to put this axis of rotation? And you can put the axis of rotation anywhere you like. And remember that Fn is actually 0. So that one's already got a torque of 0. So you could actually just ignore that one right there. Okay, so it's going to be basically this force, okay, and this force, if we put that are going to give torques if we put the axis of rotation up here, which we can do, all right, or equivalently, we could put the axis of rotation down here, in which case it'll be this force and that force that'll be counteracting. Okay, it doesn't really matter which one. Okay, we use. Let me clean that up a bit. Doesn't really matter which one. All right. I think I'll just do it down here, like I did in during the lecture, because this one is 0. All right. Because that one's 0, I really don't have to worry about eliminating it. Okay. So we've got our axis of rotation there. That means that the torque due to the ground, we can call that tau g here like that. That's going to equal 0. Why? Well, because it's acting at the point where r is equal to 0. Okay? All right. Now, the next thing is, what about the torque due to this one? Well, we need a couple of things. Okay? We're going to need the distance. Let me do this in red. We're going to need this distance, or probably blue is better. We're going to need this distance in here. Okay? Right? Because what are we calculating? We're calculating RF sine theta. Okay, so we're going to need this distance in there. Okay, that's going to be our R. Oh, let me get rid of this. Sorry, let me clean that up a bit. That's going to be our R right in there. Okay, and we're going to need this angle in there. Okay, for our theta. And you say, well, how do I get that? Well, what's the length of the entire ladder? Remember, this is 90 degrees. So the length of the entire ladder is basically going to be, let me actually just create another diagram here like this. How does that look? Good. Okay. So, if we have here the base of the ladder, which was 4, and we have the height of the ladder, which is 5, okay, and the ladder sitting like this, what does that look like? It's a right angle triangle. And how do you get that hypotenuse there? I guess let's call it, I don't know, L. How do you get that L? Well, Pythagorean theorem, right? So it's the square root of 4 squared plus 5 squared. Okay, like that. All right, it's from Pythagorean theorem. And so what's that going to equal? Let's do it on our calculator. It's the square root of 4 squared plus 5 squared, like that. And that gives me 6.40. So 6.40. Okay, and we're also going to need half of that, and half of that, of course, is 3.20. Okay, so let's switch back to the other screen, the other picture there, like that. Okay, so the distance from here, the axis, to where mg acts, that distance in there, that r, is going to be 3.2 meters. Okay, and the distance from the axis to where this one acts, up there, that distance is going to be 6.4 to there. Okay, so all right, that's part of it, but we're also going to need this angle in here. Okay, and believe it or not, we're also going to need this angle. Well, I'll draw it when we get there. Okay, let's just get this angle in here. Okay, and so this angle, you go, well, how do I get that one? Well, this angle is the same as that angle. Okay, why? Because it's, this line here is parallel to that line. Okay, let me clean that up. So you say, well, how do I get that angle? Well, let me switch back to this diagram here. How do you get that angle right in there? Okay, so we now know that L is 6.4, and there's a whole bunch of ways of getting this angle right in there. Okay, call that theta. All right, you could do adjacent, which would be 5 over hypotenuse. You could do opposite over hypotenuse, okay? And so let's just do the sine, okay? So sine of theta. And you say, well, what is that angle? What's sine? Remember that sine is defined as the opposite over the hypotenuse. So the sine is going to be 4 divided by 6.4. Okay, and then you take the inverse sine and you can get it that way. Another way, maybe this is like, let's do it this way because this is the way I did it last semester. I did tangent a lot, right? And tangent is opposite, so that's going to be 4 divided by adjacent, okay, which is going to be 5. Okay, and so theta is going to equal the inverse tangent of 4 divided by 5. And what's that angle going to be? I'll give it to you in just a second. So it's the inverse tangent of 4 divided by 5 is, looks like 38.7. 38.7, okay, 38.7, okay. And so, all right, remember that angle there, 38.7. So if we switch back to this angle right in here, that angle in there, let me just draw an arrow there. That one is 38.7. Let me just check that number again. Yeah, 38.7, okay. Now, why did we need that? So we're going to do tau due to mg is going to equal RF sine theta. R we know is 3.2. F we know is, what did I say it was? F was, I got to look it up here, 20. Okay, so it's 200. So F is 200, the weight of the thing. Okay, and sine of theta is going to be sine of 38.7. Okay, now this is getting messy here, so let me just switch to my other screen here. Okay, so the clockwise, what direction is this? That one, the direction that mg wants to turn this in is actually clockwise. Okay, now remember the axis is down here, right here. Okay, and so we're turning around that axis. mg wants to turn this thing that way. Okay, you see that, how it kind of wants to, that's not a good, kind of wants to turn it like that. Okay, because it's pulling it down, and so that's clockwise. So this torque right here, that's a clockwise torque. Okay, so let's switch back here. All right, so some of the clockwise torques. Well, what is the clockwise torque? It was RF sine theta, and R was 3.2. Is that right? Let me just take a quick look here. I forgot already. Yeah, 3.2. Okay. Oh, I'm sorry. 3.2, and F was 200, and sine was 38.7. All right. So we've actually got the one torque. Okay. And on the other side, so this is on the some of the clockwise torques. Okay. Now what about the other side? So we have to do our sine theta again for the other side, for the opposite direction. So over here we're looking at the torque up here. This is the torque due to FF. That one's a little bit harder to see, and the reason is, let me, you know what? Let me clean up a lot here. We don't need this. Let me just clean up some stuff here. All right, there we go. Okay, so the angle here, and let me see if I can draw this in blue. So remember how you get that angle? You start at the axis and you move all the way to where the force acts. Okay, and then you measure the angle between the force and that r vector there. Now that one's a lot harder to see what that's going to equal, but we know what this angle in here is. we know that that angle in there is actually 38.7. Okay, because we just got that. Now, if this is 38.7 in there, and this whole thing is 180 degrees, well then, this angle here has to be right in there. That angle there has to be 180 minus 38.7. Okay? So, admittedly, a little bit harder, but this problem is all really about the angles. It's really about the angles. Okay, so what's that work out to? Subtract 180 here. That turns out to be 141.3. So this is going to be 141.3. Okay, so what's R? Well, we start from the axis and we go to here. That distance was 6.4 meters. Okay, so there's our R. What's F? Well, we don't know F. Okay, there it is, FF. We don't know it. And what's theta? 141.3. Okay, so let's switch back to the other board and we'll put that in. Okay, so for RF sine theta here, let me just rewrite that on the line below it. Okay, so for R, that's going to be 6.4. Whoops, 6.4. Okay, F was the force of friction on the wall. Okay, and theta we said was 141.3, like that. Okay, and so this tells me that FF is going to equal. Well, let me do it in steps here. Okay, let me calculate this first so you can see what's going on. Copy. Oh, it didn't like that. This side is going to be 400. Okay. And that's going to equal, and this side is going to be 6.4 times the sine of 141.3. And what? Oh, try that again. And that's going to equal 4. This is equal to 4 FF, like that. So that tells us that FF is equal to 100 newtons. Okay, there we go. We got that it was 100 newtons, all right? So I'll finish this off and then I'll go over it again. So over here, we have this. So now substitute into equation number 1. Oops. And equation number 1 said this. And now we know that FF is 100 newtons, so guess what FG has to be? Obviously, FG also has to be 100 newtons. Okay, so there we go. We solved that problem. All right, let me take a look if there's any questions in the chat. All right, so let's switch back to the whiteboard here. So it turns out that this was a pretty easy problem because I didn't anticipate that Fn was going to fall out of the picture, but that's okay. It still has a lot of the difficulties of the geometry. Okay, so what's going on here in this problem is we have lots of mess here. Let me clean up a bit here. Clean up. And actually we can clean up some more. There we go. Yeah, that looks a lot better. Actually, we can still take out some more here. There we go. Okay, so what's going on here is this Fn here, that one you can ignore, okay? And the reason is that it's there are no forces in the horizontally, okay? So it's kind of like the lever problem. If there's only one force horizontally and it's unbalanced, then in other words, if Fn were not 0 there, okay, if Fn were like 10, then it would start to accelerate in that direction, okay? So that immediately tells us that Fn is going to be 0, all right, in this situation, all right? Now, the other forces, though, they are up and down. Okay, they're in the y direction. They have to balance, because if there's an excess force up, then this thing would actually start to accelerate up. Or if there's an excess force down, then they would start to accelerate down. So that force, and that force, they have to balance. Okay, these two are up, so they add together, and that one is down, and so these two, FF plus FG, I guess I could write it over here, FF up plus FG up. Okay, they have to balance this one, and this one we know to be 200 newtons. Okay, there we go. But you could see that, this doesn't solve the problem, because you still don't know that one or that one. Okay, you know that together they have to be 200, but you can't work it out. Yeah, you can't determine one without knowing the other. Now, the next thing is choosing an axis of rotation. Doesn't matter which one you choose, all right? But if you choose like this one down here, where we at the ground like that, well, then you have to identify. Remember, this one is out of the picture. You have to say, well, what forces are going to give you torques? Well, this one's not going to give you a torque, because it's acting right at the axis. And to give you intuition why, I mean, I know the formula is RF sine theta, but the way you could think about this is that, like, imagine if you try to turn something by pushing on the hinges, pushing on the point around which it's going to turn. Well, that doesn't work. So, you don't turn a door by pushing on the hinges. So you're like imagining that this thing actually could turn around that point. Well, by pushing there, you're not going to actually turn it. Okay. And so that one doesn't have a torque. This one's out of the picture, as we said already, because there's nothing to balance it. And so there's only two forces left. There's that one and that one. Okay. This one, the gravitational force, imagine again that it wants to turn around here. This one, I know it's not pulling straight perpendicular like that. Okay, it's pulling down. But if you turn off all the other forces, if you just pull down there like that, and there were no other forces on this thing would want to start turning that way around that pivot point. Okay, that axis. All right. This one, on the other hand, again, imagine there's no other forces, and you're just going to pull up on this ladder like that. Okay, again, it's not exactly perpendicular to the ladder, but still pulling up has enough of a component perpendicular that's going to make it want to turn that way. So FF wants to turn it that way, MG wants to turn it that way, and there are your two torques. This torque, okay, wants to balance this torque. All right, whoops, there we go, like that. Okay, so those two torques want to balance one another. So you just calculate RF sine theta. That's where the difficulty came in calculating RF sine theta, because you needed R, this distance right in there, and you go, I don't have that. I know, but you have this. Well, you can calculate that distance in there, because it's the square root of 4 squared plus 5 squared. Okay, so this is where the geometry comes in, and I think that's what makes this problem hard. Okay, so once you use Pythagorean theorem, you've got this distance there of 6.4. Okay, and then of course that means that this distance here is 3.2, half of 6.4, obviously. Okay, if I didn't mention that before, whoops, let me write that again. 3.2 meters. Okay. That's half of 6.4, but it's still not enough or not complete, because you also need that angle there. And you go, how do I get that angle? Well, that angle there is the same as that angle there. Okay, and you say, well, now how do I get that angle? Okay, that angle, you could say, well, the tangent of that angle, you can form any one of the trig identities that you like, but last semester we used tan a lot. So remember what tangent is? Tangent is the opposite divided by the hypotenuse, divided by the adjacent. Okay, so whoops, so tangent of theta is going to be opposite, which is 4 divided by 5, and that turned out to be, what was it, 38.7, whoops, 38.7 degrees, like that. And so now we have R 3.2, we have F 200, and we have 37 degrees, and that gave us, let me clean this up. That gave us this torque. Okay, that had to balance this torque. And that one was even, I think, a little bit harder. We now know that this angle in here is 38.2, but that's not the angle we want. We want this angle in there. Okay, we know that that angle plus that angle has to equal 180, right? And so that angle was 180 minus the 38.7. Okay, so the problem was really a lot of geometry. All right, and these ladder problems tend to be a lot of geometry problems, a lot of geometry work. But still, it's, you know, the physics there is, I hope, straightforward. It's going to be this torque there balancing that torque down there. Okay, and let's switch back here, and that's what I did right here. Okay, so I had r of sine theta on the one side was equal to r of sine theta on the other side. Okay, now this one was the r of sine theta due to mg, and this one's the r of sine theta due to uh, no, not g, force of friction, like that. Okay, and we we knew all of the quantities here, and on this side we knew almost everything except for FF, and so we could solve for FF, and then that gave us, with equation 1, gave us FG. Okay, so yeah, a little bit harder, but I wanted to do a harder problem. Okay, I guess another variation on this, this is the last thing I'll say, and then I think we're done for the evening. Another variation on this that would have made it more easy, more interesting, was remember that Fn was 0, and here, let me clean this up again. Okay, let me clean it up some more. Clean it up some more. Okay, I might have said, you know what? There is a little bit of friction down here. Okay, and let's call that FGF. Okay, now I'm not going to solve this, but let's just in principle say what we would have done. Well, now we can't say that the forces in the x direction cancel, or zero. You know, sorry, we can't say, well, you know, there's only one force in the x direction and therefore it must be 0. Okay, now what we have is that this Fn here would have to balance that one there, and so we would have an additional formula. We would have to have Fn is equal to force of the ground friction. Okay, and so that would have been our x component forces balancing. Our y component forces balancing would have been FF plus FG is equal to FF plus FG is equal to 200. And then the torque formula, I won't write it, but it's the same torque formula that we did a minute ago. Because if we choose the axis of rotation down here, then this has no torque, but this one has no torque as well. Okay, so you know, if I'd actually solved this problem beforehand, I probably would have added just another force there, and it would have been a little bit more similar to the one that we did in the during the pre-recorded lecture. Okay, if there are no questions, then I think that's it for static equilibrium. All right. I'll just wait a second to see if there's any questions in the chat. Let me just see. There's a bit of a lag, so else we're done. I hope that was useful. By the way, on the assignment, I have a ladder problem, but it's not like this one where I have friction up at the it's not like this one where I have the friction up on the wall. It's actually like the friction is on the ground. All right, I don't see any questions, so let me just say goodbye.